Good morning everyone. Today we are going to start the chapter organometallic compounds. Introduction. An organometallic compound is a compound which contains at least one carbon metal bond in its molecule. The metals present in these compounds are generally reactive metals such as lithium, sodium, magnesium, zinc, and lead. The organic part consists of alkyl, alkenyl, alkynyl, or aryl group. The carbon metal bond is essentially a polar covalent bond. The extent of polar or ionic character of the bond depends upon the electropositive nature of the metal. More electropositive the metal, the more ionic the carbon metal bond. Thus, the ionic character of carbon metal bond is in the order carbon potassium, carbon sodium, carbon lithium, carbon magnesium, carbon aluminium, carbon zinc, and carbon cadmium. The reactivity of organometallic compounds, in turn, depends upon the ionic character of the metal carbon metal bond. More the ionic character of the bond, the more reactive the organometallic compound. Naming of organometallic compounds. Organometallic compounds are named by adding the name of metal to that of organic group. For example, methyl lithium, phenyl lithium, diethyl cadmium, organomagnesium halides are named as alkyl or aryl magnesium halides. For example, methyl magnesium iodide, phenyl magnesium bromide. In this chapter, we shall discuss the chemistry of organomagnesium, organolithium, and organozinc compounds. First, organomagnesium compounds, the Grignard reagents. Organomagnesium halides is popularly known as Grignard reagents are the most important of all organometallic compounds. They were discovered by Victor Grignard, who received the Nobel Prize in 1912 for this discovery. The general formula of the Grignard reagent can be represented as RMgX, where R is alkyl, alkenyl, alkynyl, or aryl group, and X is Cl, bromine, or iodine. Organomagnesium fluorides are practically unknown. Preparation of Grignard reagents. A Grignard reagent can be prepared in the laboratory by the action of alkyl or aryl halides on magnesium metal in the presence of dry ether. For example, ethyl bromide plus magnesium in the dry ether gives ethyl magnesium bromide. In place of ether, other solvents such as tetrahydrofuran (THF), triethylamine, dioxane, dimethoxyethane, or dimethyl ether of ethylene glycol have also been used. In fact, THF is considered to be the best solvent as it increases the reactivity of alkyl or aryl halides toward magnesium. Grignard reagents of aryl and alkyl halides, which are less reactive, are usually prepared in THF. Procedure. The alkyl or aryl halide is taken in a dropping funnel fitted to the mouth of a flask containing magnesium turnings covered by a layer of dry or THF. The halide is then added slowly to the flask with simultaneous shaking of the flask. A vigorous reaction takes place and magnesium metal gradually disappears, forming a cloudy solution. This solution constitutes Grignard reagent, which is used as such for various reactions. If in a particular case formation of Grignard reagent does not take place easily, addition of 1 or 2 drops of methyl iodide help in initiating the reaction. This is called entertainment technique. In general, for a given alkyl or aryl group, the ease of formation of Grignard reagent is in the order Ri, Rbr, Rcl. On the other hand, for a given halogen, the ease of formation usually decreases with increase in the number of carbon atoms in the alkyl group. Important precautions. The following precautions must be observed during the preparation of Grignard reagents. First, the apparatus used must be dry and moisture proof. Second, all the reactants used in the preparation, that is alkyl or aryl halide, ether and magnesium, must be absolutely dry and pure. Third, ether used as a solvent must be completely free from alcohol. Fourth, it is also desirable to maintain an atmosphere of nitrogen free from oxygen and carbon dioxide during the preparation. These precautions are necessary because Grignard reagents are highly sensitive to moisture and also react with oxygen and carbon dioxide. The ethereal solution of Grignard reagent obtained above is generally used as such for different reactions. Mechanism. The mechanism of formation of Grignard reagent is still not known with certainty. However, it has been suggested by Gumberg and Beckmann that the reaction starts with the formation of small amount of magnesium halide and then proceed by a free radical mechanism. Structure of Grignard reagents. The Grignard reagents are usually represented as RMGX. It is believed that the carbon-magnesium bond is covalent but highly polar, while magnesium-halogen bond is essentially ionic. But the representation does not stand for the actual molecule. It has also shown It has been shown that during the preparation of Grignard reagent, ether does not merely provide a medium for the reaction. On the other hand, it helps in the dissolution of magnesium by solvation. Accordingly, it has been suggested that ether gets incorporated as a part of molecule. This ether may be termed as ether of crystallization. Structure 1 shows Grignard reagent in the monomeric and having coordination with the two molecules of ether used in solvation. Structure 2 represents Grignard reagent as a 1:1 complex of dialkyl or diaryl magnesium and magnesium halides. This is coordination between the two halogens of magnesium halide and the magnesium atom of dialkyl or diaryl. At the same time, two molecules of either ether coordinate with the magnesium and magnesium halide. It has also been suggested that the following equilibria are possible for Grignard reagents in ether. It may be pointed out, however, that while writing the reactions of Grignard reagent, their general formula is still represented as RMGX for the sake of convenience. Physical properties of Grignard reagents. Grignard reagents are non-volatile colorless solids. Due to their explosive nature, they are seldom isolated in the free state but are used in the solution form in the solvent in which they are prepared. Chemical properties. Synthetic application. The carbon-magnesium bond in Grignard reagent is about 35% ionic. Therefore, Grignard reagent can be written as RMGX. The negatively polarized alkyl group can act as a carbanion or as nucleophile. It would attack other molecules at sites of low electron density. Therefore, the main reactions of Grignard reagents are nucleophilic substitution and addition reactions. Reaction with compounds containing active hydrogen, formation of hydrocarbons. An active hydrogen means a hydrogen which is more acidic than the hydrogen in alkanes. The compounds containing active hydrogen such as water, alcohol, carboxylic acid, amines, and terminal alkynes react with Grignard reagent to form hydrocarbons. Reactions of Grignard reagent with compounds containing active hydrogen result in the formation of hydrocarbon in quantitative yield. This forms the basis of Zarivitinov method of estimation of active hydrogens. Second, alkyl magnesium halides formed in the last reaction can be further used for preparation of higher alkynes by reaction with alkyl halide. Aryl magnesium halides also undergo similar reactions to form aromatic hydrocarbons. Other nucleophilic substitution reactions. Due to only weak negative polarization of carbon of alkyl or aryl groups in the Grignard reagents, these reagents act as only weak nucleophiles. They do not undergo nucleophile substitution with simple alkyl halides. However, compounds containing more reactive halogens undergo substitution reaction with Grignard reagents as given below. First, reaction with more reactive alkyl halides. Formation of alkanes. Grignard reagents react with more reactive alkyl halides such as tertiary butyl chloride to form higher alkenes. Reaction with the reactive unsaturated halides. Formation of alkenes. It may be pointed out that Grignard reagents do not react with unsaturated halides of low reactivity such as vinyl halides. Reaction with lower halogenated ethers give rise to the formation of higher ethers. Reaction with iodine. Alkyl magnesium chloride or bromides react with iodine to form alkyl iodide. This reaction can be used for converting an alkyl chloride or bromide into corresponding iodide via the formation of Grignard reagents. Reaction with inorganic halides leads to the formation of organometallic compounds. Reaction with ethyl orthoformate. Formation of aldehydes. When treated with ethyl orthoformates, Grignard reagents form acetals which on hydrolysis gives aldehydes. Reaction with chloramine gives rise to the formation of primary amines. Nucleophilic addition reaction. Grignard reagents undergo nucleophilic addition reactions with compounds containing multiple bonds such as carbonyl cyano group. The addition products thus formed are easily hydrolyzed in acidic medium to furnish a large variety of product. In these reactions, the nucleophilic group of RMGX, that is alkyl or aryl group, gets attached to the electropositive end of the multiple bond, while MgX group gets bonded to the electronegative end. The important nucleophilic addition reactions are described below. First, reaction with carbonyl compound. Grignard reagents react with carbonyl compounds such as aldehydes, ketones, esters, acid, chlorides, and anhydrides to form addition products in which the alkyl or aryl group of Grignard reagents get bonded to carbonyl carbon, while the remaining part of the Grignard reagents get attached to the oxygen. The addition complex thus formed is hydrolyzed by water in an acidic solution to form alcohols. Reaction with formaldehyde gives rise to the formation of primary alcohols. Reaction with aldehyde other than formaldehyde give rise to the formation of secondary alcohols. Reaction with ketones give rise to the formation of tertiary alcohols. It may be noted that in the above reactions, the number of carbon atoms in the alcohol is equal to the carbon atoms in the Grignard reagent and aldehyde or ketone. Reaction with ester. Formation of secondary and tertiary alcohols. Reaction of Grignard reagents with ester of formic acid yields secondary alcohols, while the ester of other acids, tertiary alcohols, are produced. The reactions take place in two stages. An aldehyde or ketone is initially formed which reacts further with Grignard reagent to form alcohol. It may be noted that in tertiary alcohol formed at least two alkyl groups would be similar. It can easily be seen that if Grignard reagent is treated with an ester in the ratio 1:1, the reaction can be stopped at the aldehydic or ketonic stage. Reaction with acid chlorides and anhydrides give rise to the formation of tertiary alcohols. Grignard reagents 2 moles react with acid chlorides or anhydride 1 mole to yield tertiary alcohols. The reactions take place in 2 stages. If equimolar amounts of Grignard reagent and acid chloride or acid anhydride are used, ketones can be obtained as the reaction product. Other reactions. Grignard reagent undergoes some other important nucleophilic addition reaction forming various products. First, reaction with nitriles, formation of ketones. Grignard reagent reacts with nitrile to produce a ketimine which undergo hydrolysis to form a ketone. If Grignard reagent is treated with HCN in place of nitrile, an aldehyde is obtained by the hydrolysis of the adduct initially formed. Reaction with ethyl chloroformate give rise to the formation of esters. Reaction with carbon dioxide give rise to the formation of monocarboxylic acids. Reaction with sulfur dioxide give rise to the formation of sulfenic acid. Reaction with carbon disulfide give rise to the formation of dithionic acids. Reaction with epoxides give rise to the formation of primary alcohols. It may be noted that alcohol obtained contain 2 carbon atoms more than the Grignard reagent in this case. Reaction with oxygen give rise to the formation of alcohols. Reaction with sulfur give rise to the thioalcohols. Abnormal behavior of Grignard reagents. First, reaction with ketones. In the reaction between Grignard reagent and ketones, branching of carbon chain at the alpha carbon or carbonyl group or presence of bulky group in the Grignard reagent sometimes prevent the normal addition reaction from taking place at all due to the steric hindrance. In some other cases, a totally unexpected reaction may take place. For example, when isopropyl magnesium bromide is added to diisopropyl ketone, the expected tertiary alcohol triisopropyl carbinol is not formed. On the other hand, diisopropyl ketone undergo reduction to form diisopropyl carbinol. This unexpected reaction is attributed to the transfer of a hydride ion from Grignard reagent via a 6-membered cycle transition state, as in the case of Merovin-Pondervoff-Varley reduction of ketones. Reaction with alpha and beta unsaturated carbonyl compounds. Grignard reagents do not react with simple alkenes, but they can react with alpha beta unsaturated carbonyl compounds to give products both from initial 1,2 and 1,4 addition. In other words, the overall addition may take place at carbon oxygen bond 1,2 addition or carbon carbon double bond 1,4 addition. Synthetic utility of Grignard reagents. Grignard reagents are rated as one of the most important reagents used in synthetic chemistry, as is apparent from the large variety of organic compounds which can be obtained with their help. The main class of organic compounds which can be prepared from them are summed up below. First, hydrocarbons, Second, alkyl iodides. Third, alcohols, primary, secondary, as well as tertiary. Ethers, aldehyde and ketones, carboxylic acids, primary amines, ester, thioalcohols, sulfenic acids, dithionic acids, and other organometallic compounds. Limitations of Grignard reagents. In spite of their extreme utility in synthetic organic chemistry, Grignard reagents suffer from the following limitations. First, Grignard reagents are rather difficult to handle because they are highly sensitive to moisture, oxygen, carbon dioxide, etc. Second, alkyl or aryl halides used in the preparation of Grignard reagents must not contain active substituent groups such as OH, NH2, COOH, CHO, CO, CN, since they can themselves easily react with Grignard reagents. Third, the compounds with which Grignard reagents are to be reacted should also not contain any reactive group other than the one at which the reaction is desired. Otherwise, many undesirable side reactions may take place. Fourth, in case of compounds containing branching near the functional group of or Grignard reagent containing bulky group, the reaction sometimes does not take place due to steric hindrance. Fifth, nitro compounds cannot be used in Grignard synthesis because they oxidize the Grignard reagents. Now moving toward organolithium compounds. Organolithium compounds are the most important of organometallic compounds derived from alkali metals. They may be represented by the general formula RLI, where R may be an alkyl or aryl group. Some of the more commonly used organolithium compounds are methyl lithium, ethyl lithium, N-butyl lithium, phenyl lithium. The carbon lithium bond is covalent but strongly polar in character. Preparation of organolithium compounds. Organolithium compounds are usually prepared by the following methods. First, reaction between lithium and alkyl halides. Alkyl lithiums are generally prepared by the reaction between alkyl halide and lithium metal at low temperature in trihexane or benzene solvent and an inert atmosphere of nitrogen or argon. Ether is not generally used as a solvent for the preparation of alkyl lithiums due to the possibility of Wurtz reaction and other side reactions. Second, by metal exchange reactions. Alkyl lithiums can be readily prepared by the action of lithium or organometallic compounds of a less reactive metal such as mercury. By exchange reaction, aryl lithiums are generally prepared by treating aryl halides with an alkyl lithium. Physical properties. Due to strong polarization of carbon-lithium bond and small size of lithium, organolithium compounds exist as dimer or higher aggregates of molecules. They are colorless liquids or solids with low melting points. They are highly soluble either in ether and hydrocarbon solvents. Chemical properties, synthetic applications. Carbon lithium bond present in organolithium compounds has a greater ionic character than that of carbon magnesium bond in Grignard reagents. Therefore, the former are more reactive than Grignard reagents, although both resemble each other in most of their reactions. The important reaction of organolithium compounds are as given below. First, reaction with substances containing active hydrogen give rise to the formation of hydrocarbons. Second, reaction with carbonyl compounds. It gives rise to the formation of alcohols. Third, Like Grignard reagent, organolithium compound react with carbonyl compound to form primary, secondary and tertiary alcohols. Due to their smaller size, there is a less steric hindrance involved in the reaction of organolithium as compared to Grignard reagent. While Grignard reagents do not react with ketones containing bulky groups, organolithium do so to form tertiary alcohols. Reaction with epoxides, formation of alcohols. They react with ethylene epoxide to give primary alcohols. Reaction with carbon dioxide, formation of carboxylic acid and ketones. Organolithium reacts with equimolar proportion of carbon dioxide to yield carboxylic acids. If excess of organolithium is used in this reaction, a second molecule of organolithium can also add to carboxylate anion formed in the first stage and lead to the formation of ketones. It may be pointed out that being relatively less reactive, Grignard reagents do not react further to give ketones. Reaction with alkenes, formation of long chain alkanes. Unlike Grignard reagents, organolithium can add to carbon-carbon double bond at high pressure. This reaction can be used for preparing long chain alkanes as the process can continue indefinitely. Reaction with hydrogen cyanide or orthoformate give rise to the formation of aldehydes. Reaction with nitrile or orthoesters other than orthoformic ester give rise to the formation of ketones. Reaction with lower halogenated ethers. Formation of higher ether take place. Reaction with cyanogen chlorides give rise to the formation of nitriles. Reaction with alkyl halides, it gives rise to the formation of alkanes. Being more reactive than Grignard reagents, organolithiums can undergo nucleophilic substitution even with alkyl halides. Reaction with aryl halides and heterocycle compounds. This reaction takes place by elimination addition mechanism involving the formation of naphthyene intermediate. Reaction with alpha beta unsaturated carbonyl compounds. Organolithium undergo 1,2 addition at the carbonyl function of alpha beta unsaturated carbonyl compounds to yield ultimately unsaturated alcohols. Grignard reagents undergo both 1,2, 1,4 addition with alpha beta saturated carbonyl compound. It may be seen that in the second stage of reaction, 4 and reaction 5, 10 and 12 organolithium differ from Grignard reagents. Organozinc compounds. Organozinc compounds were the first organometallic compounds to be prepared in laboratory. They are milder reagent as compared to organolithium compounds or Grignard reagent. Some of the commonly used organozinc compounds are dimethyl zinc, diethyl zinc, diphenyl zinc. Preparation of organozinc compound. Organozinc compound are generally prepared by the following methods. First, from alkyl halides. On treatment with zinc fillings, alkyl iodides form alkyl zinc iodides. These undergo disproportionation reaction or distillation in an atmosphere of carbon dioxide to yield dialkyl zinc compounds. From organoaluminium compounds. When treated with zinc chloride, organoaluminium compounds give rise to organozinc compounds. Physical properties of organozinc compounds. Organozinc compounds are non-polar, low-boiling liquids or low-melting solids soluble in organic solvents. This is because they have linear geometry due to sp hybridization of zinc atom. The lower organozinc compounds are highly inflammable for the reason they are generally prepared and used in the atmosphere of carbon dioxide. Chemical properties, synthetic applications. As stated above, organozinc compounds are milder reagents than organolithium compounds and Grignard reagents. As such, their reactions take place rather slowly. The main reactions of organozinc compounds are given ahead. First, reaction with water give rise to the formation of hydrocarbons. Reaction with alkyl halides give rise to the formation of hydrocarbons containing quaternary carbon atom. Organozinc compounds react with tertiary alkyl halides, not with primary or secondary alkyl halides, to form hydrocarbons containing quaternary carbon atom. Reaction with acid chlorides give rise to the formation of ketones. Reformatsky reaction, formation of beta hydroxy esters. This reaction consists in treating an aldehyde or a ketone with an alpha bromoester and metallic zinc in the presence of dry ether or benzene. An organozinc compound is the first formed which adds to the carbonyl group to give an addition product. The addition product thus formed is decomposed in the presence of dilute minerals acid to yield beta hydroxy esters. Iodomethylene zinc iodide. It is an organozinc compound which is mainly used in the formation of cyclopropane derivatives from alkenes. The reaction known as Simon-Smith reaction is carried out by treating alkenes with methylene iodide and a zinc copper couple to get cyclopropane derivative. Hence, this was our chapter. Thank you.